Welcome, welcome, welcome to Astronomy Daily, your go-to source for everything happening beyond our blue planet. I'm Anna.
And I'm Avery. We're so glad you could join us today for what promises to be a fascinating journey through the cosmos. We've got a packed show lined up, delving into some truly mind-bending discoveries and exciting news from across the solar system and beyond.
That's right. We'll be unraveling the peculiar mysteries of Uranus and its moons, exploring a newly mapped cosmic bubble surrounding our solar system, and getting you up to speed on one of the busiest launch weeks we've seen this year.
And stick around for what could be a groundbreaking discussion on how life might thrive in the most unexpected dark corners of the universe. It's a fresh perspective that challenges everything we thought we knew about habitability. So let's dive right in.
All right, Avery, let's kick things off with a planet that truly lives up to its reputation for being a bit, well, weird. We're talking about Uranus, the seventh planet from the sun, which has always stood out from its solar system siblings.
It really does. While most planets spin fairly upright and their moons orbit neatly, Uranus is just doing its own thing, tilted on its side at a whopping 98 degrees. Imagine Earth's North Pole pointing towards, say, the constellation Ophiuchus instead of Polaris. That's Uranus for you.
And it's not just its tilt. Its magnetic field is also off-kilter, differing by 59 degrees from its spin axis. That's like our magnetic poles being in Perth, Australia, and northern Florida, which is quite the cosmic anomaly.
This peculiar setup led astronomer Christian Soto and his team at the Space Telescope Science Institute to study how Uranus's magnetic field might interact with its four largest moons, Ariel, Umbriel, Titania, and Oberon.
You'd expect that because Uranus rotates faster than its moon's orbit, its magnetic field would catch the moons from behind and bombard their trailing sides with radiation. This process, called radiolysis, should create dark compounds, making those trailing sides appear darker in ultraviolet light.
But here's where it gets truly puzzling. When the Hubble Space Telescope peered at these moons, it found the exact opposite. For Ariel and Umbriel, there was hardly any difference between their leading and trailing sides. And for the outer two moons, Titania and especially Oberon, it was their leading sides that were darker.
This was completely startling to the researchers. It suggests that Uranus's magnetosphere might not be as active as previously thought, or it's far more complex. But the darkening on the leading sides points to another process entirely.
And that process, Soto suggests, involves Uranus's irregular moons. These are smaller, often captured asteroids with unusual, highly tilted orbits. The theory is that micrometeorites constantly hit these irregular moons, ejecting dust into their orbits.
Over millions of years, this dust drifts inward, crossing the paths of the major moons. As the major moons orbit, they sweep up this dust, primarily on their leading hemispheres. Soto likens it to driving fast on a highway and bugs hitting your windshield.
And the outer moons, Oberon and Titania, likely shield the inner ones, Ariel and Umbriel, from this dust. But even within the outer pair, there's still a mystery. Why is Oberon getting so much more dust than Titania? That's still one of the weird findings they're trying to figure out.
This fascinating research highlights how much more there is to learn about our own solar system. Soto hopes for a dedicated mission to Uranus in the future, perhaps in the early 2040s, to truly unravel these mysteries. After all, as he put it, it is very weird, so why not?
From the mysteries of our own solar system, let's zoom out a bit to our cosmic neighborhood. Our solar system isn't just floating in empty space. It resides within a massive million-degree hot bubble of incredibly thin gas. It's called the local hot bubble, or LHB.
This LHB is essentially an invisible cocoon that glows in X-ray light and stretches over 1,000 light years across. And remarkably, despite its scorching temperature, its sparse atoms barely affect the surrounding matter. Some scientists even suggest this quiet warmth might have helped life flourish on Earth.
For decades, the true shape and origin of this bubble remained a puzzle, but now, thanks to the sharp-eyed Erocita X-ray telescope and a team of scientists in Germany,
The picture is finally coming into focus.
The Max Planck Institute for Extraterrestrial Physics led the effort using Erocita to map the LHB in unprecedented detail. What made this telescope so crucial is its position far from Earth's atmosphere, allowing it to capture clear, soft X-ray emissions without interference from our own planet's solar-wind interactions.
And the findings? Well, the LHB is far from a smooth sphere. Lead researcher Michael Young described it as spikier and bumpier, with an irregular, jagged shape that bulges unevenly. It expands more freely towards the galactic poles, avoiding the denser midplane of the Milky Way, which makes sense as hot gas moves towards less resistance.
This lumpiness likely reflects the chaotic forces that shaped it, such as multiple overlapping supernova explosions and feedback from other stars. But perhaps the most surprising discovery was a previously unknown tunnel stretching towards the constellation Centaurus.
This interstellar passage may connect the LHB with the neighboring superbubble, acting like a cosmic gateway. As co-author Michael Freyberg explained, the existence of this tunnel carving a gap in the cooler interstellar medium was completely unknown until Erocita's sharper sensitivity revealed it.
This new data from Erocita also helped settle a long-standing debate. Scientists had proposed the LHB concept over 50 years ago to explain faint X-ray readings. But doubts arose in the 90s when similar X-rays were found to originate from solar wind interacting with Earth's atmosphere. Erocita's clear observations confirmed that much of that soft X-ray background truly comes from the LHB.
And the team also found a temperature difference across the bubble, with the southern part being warmer than the northern side. This could point to recent heating events, perhaps new supernovas in the last few million years, suggesting the LHB isn't just a leftover, but an active, changing part of our galactic landscape.
And the idea of the Centaurus tunnel suggests it might be just one part of a larger system of tunnels, like arteries running through the galaxy. These gaps between cold clouds could link the LHB to distant features like the Gum Nebula or other superbubbles, indicating the Milky Way is an interconnected structure constantly shaped by explosive energy.
It's truly mind-boggling to think about. The team even mapped dense molecular clouds at the edges of the bubble, some moving outward as if pushed by the original explosions that carved out the LHB. And fascinatingly, our sun is thought to have entered the LHB only a few million years ago, a mere blink in its 4.6 billion year lifespan.
The 3D model they built paints a vibrant, layered picture of our solar system's galactic neighborhood, including supernova remains, molecular clouds, dust, and these newly discovered tunnels. Mapping this cosmic web could provide incredible insights into how stars die, galaxies evolve, and how material moves between star systems.
It's a major step in understanding not just our immediate bubble, but the dynamic, often explosive forces that shape the space between stars. It's like finding a secret highway system in space right outside our galactic door.
Well, from cosmic bubbles and planetary tilt, let's bring it back to Earth for a moment and look at the immediate future of space travel. We have a packed week of launches ahead.
It's truly bustling, Anna. This week's launch manifest is one of the busiest of 2025 so far, with 10 launches scheduled from around the world. We're talking everything from crewed missions to secret government payloads.
Kicking things off on July 29th, iSpace's Shuanghuxian-1 rocket is set for its 8th flight from China after a year-long hiatus following a failure on its 7th mission. The payload for this one is currently unknown, but iSpace is clearly hoping this launch will restore some reliability to their rocket.
Then, later that day, SpaceX is launching its first batch of Starlink satellites this week, Group 10-29 from Cape Canaveral. Falcon booster B1069 will be making its impressive 26th flight after a quick 37-day refurbishment. That's a true workhorse.
China's CASC has a launch on July 30th with their Changzheng 8A. carrying an undisclosed number of Guowang communication satellites. These are part of China's planned mega constellation of internet satellites aiming to rival SpaceX's Starlink, at least within China.
Also, on July 30th, we have a significant international mission. The joint NASA-ISRO Synthetic Aperture Radar, or NISAR, satellite. This satellite is set to map Earth's elevation multiple times a month, focusing on ecosystem disturbances like earthquakes, tsunamis, volcanoes, and ice sheet collapses.
NASA is contributing the L-band radar and a high-rate telecommunications system, while ISRO is providing the satellite bus, the S-band radar, and the launch services from India. It's a great example of global collaboration in space science.
Later that same day, SpaceX is back at it with another Starlink launch, Group 13-4 from Vandenberg. This flight will mark Falcon's 500th recovery attempt, really underscoring SpaceX's commitment to reusability.
And speaking of secretive payloads, Rocket Lab is launching a suborbital mission called Jake-4 on their HASTE testbed. This is a highly secretive government payload believed to be a hypersonic re-entry missile. Rocket Lab has completed 3 HASTE missions so far, showing a growing demand for launching payloads to suborbital space at hypersonic speeds.
Another unknown payload is scheduled to launch from China on July 31st with X-Pace's Kuaizhou 1A rocket, making its 30th mission.
But perhaps the biggest highlight of the week is SpaceX and NASA's Crew 11 mission to the International Space Station on July 31st. 4 astronauts, including NASA's Zena Cardman and Mike Finke, JAXA's Kamiya Yui, and Russian cosmonaut Oleg Platonov, will head to the ISS for a 6-month mission of science and research.
And, of course, in true SpaceX fashion, the booster B-1094 will attempt a return-to-launch site landing, and the Crew Dragon capsule Endeavour will be flying to the ISS for the 6th time after 515 days of refurbishment.
Wrapping up the week, SpaceX has a 3rd Starlink mission on August 2nd, and then on August 4th, another Chinese Chang'e 12 rocket will launch from Wingchun carrying more Guowang satellites. Given that this is the 2nd launch of Guowang satellites this week, it looks like China is pushing hard to expand its constellation rapidly, aiming to fulfill its goal of 13,000 satellites and provide reliable internet for its people. It's certainly going to be a busy week for space watchers. From the incredible pace of launches, let's shift our focus to something even more fundamental, the very definition of where life can exist. A groundbreaking new study is challenging our traditional views on habitability, proposing that life doesn't always need sunlight to thrive.
That's right, Anna. This study, led by Dimitra Atri at NYU Abu Dhabi, suggests that high-energy radiation from deep space, specifically galactic cosmic rays, could actually support life in dark, underground environments on planets like Mars and moons such as Europa and Enceladus. It really flips the script on what makes a planet or moon livable.
It's fascinating because we usually associate ionizing radiation with harm, damage to cells, DNA, and proteins. Space agencies even consider cosmic rays a major threat to astronauts. But this research highlights another side. In certain environments, radiation doesn't just destroy, it creates.
Exactly. When these energetic, charged particles hit ice or rock, they can break apart water molecules in a process called radiolysis. This reaction releases electrons and other useful products. On Earth, we found bacteria in deep South African gold mines that use these electrons as an energy source, much like plants use sunlight for photosynthesis, thriving kilometers below the surface without any light at all.
So Atri's team used a physics simulation tool to calculate how much energy cosmic rays could deposit beneath the surfaces of Mars, Europa, and Enceladus. They then estimated how much of that energy could support life, leading to a new concept they call the RHZ, or radiolytic habitable zone.
This RHC shifts the focus away from the traditional Goldilocks zone, that sweet spot around a star where temperatures allow for liquid water.
Instead, the RHZ looks underground, at places where water ice and cosmic radiation combine to create energy-rich environments. It depends on how much radiation penetrates a planet's thin atmosphere or icy shell, and how deep it can reach.
Their simulations showed that Saturn's moon Enceladus actually had the greatest potential to support life through radiolysis, with Mars following closely and Jupiter's moon Europa coming in third. These icy bodies, often thought of as lifeless because of their cold, sunless surfaces, could harbor dense underground ecosystems fueled by this radiation.
And the key here, as with so many discussions about extraterrestrial life, is water. Even small pockets of liquid water underground would allow these chemical reactions to happen more easily, providing a medium for complex molecules to form and react. It means those suspected oceans beneath the ice of Europa or Enceladus could be prime locations for alien life, powered by cosmic rays hitting the surface ice.
This study truly broadens our definition of habitability. Life might not need warmth from a star or even geothermal heat from a planet's core. Cosmic rays, long feared, could actually be a life-giving energy source in the right conditions.
It completely redefines where we might look next. Instead of just focusing on warm, sunlit worlds, we can now consider cold, dark places, as long as they have some water beneath the surface and are exposed to cosmic rays. It offers hope that the universe may be teeming with life, quietly thriving in hidden oceans powered by the stars themselves.
What an episode, Avery. We've journeyed from the puzzling mysteries of Uranus and its strangely dark moons, which are still baffling scientists, to the incredibly dynamic local hot bubble surrounding our solar system.
It's been a whirlwind, and let's not forget the sheer excitement of this week's launch roundup, with so many missions heading into space, including crewed flights and groundbreaking Earth observation satellites.
Absolutely, but perhaps the most mind-bending discussion was about the radiolytic habitable zone, pushing the boundaries of where life could exist beyond our traditional sun-drenched views. It really makes you rethink what's possible out there.
It certainly does. It's been a privilege to share all this incredible space and astronomy news with our listeners today. Don't forget, if you want more news and commentary from us, simply visit astronomydaily.io.
We hope you enjoyed exploring the cosmos with us on Astronomy Daily. Thank you for tuning in, and we look forward to sharing more cosmic insights with you in our next episode, which will be tomorrow, of course. Until then, keep looking up.